This is my team's early season robot for the Vex Robotics 2018 to 2019 season. Continuing the theme of strange names of Vex robots, this robot has been dubbed Butternut Squash. This robot was a fairly early season build, coming together in mid-October. The robot was built in about 3 days of solid work before a spur-of-the-moment tournament and was continually updated throughout the season. The robot is a dual flywheel, which was taken from the camp bot I made over the summer, with a lot of improvements. This helped take this design from a fairly good bot in the early season to being a non-meta powerhouse. I don't have any footage of the first iteration, but it was budgeted so as to have enough motors for a lift. This didn't fit with the wide flywheel design, so we ended up skipping it and adding the 2 motors to drive. This drivetrain was designed to have a lot of clearance to facilitate climbing the platform more easily. Climbing was made easier by adding extra wheels in the center of the drivetrain. The robot also used a new hold function built into the V5 system to create a brake that helped the robot stay parked on the center platform. Intakes are important, and this robot took everything good about the CampBot intake and took it up to 11. This robot used a wider intake, which allowed easier intaking, along with cap flipping if run inverted. The balls were funneled using what I have termed asymmetric intake design, which forces one ball to the center of the intake first in hopes of being able to intake 2 balls in parallel. I can freely admit that this design isn't perfect, but it does work at least marginally better than the non-asymmetric design. Non-slip mat is used to help the rubber bands grip the ball more and prevent the ball from simply spinning in place. The rubber band roller forms the first stage of the intake, feeding into the second stage, an inverted conveyor belt that pushes the ball into the flywheel. Both stages are powered by the same motor, and this brings us to the only part of the robot that I'm not completely satisfied with, the chain connecting the 2 parts. Early in the season, we had no support on the outside of the sprocket, which allowed the chain to come off, which basically crippled the robot when it happened. We remedied this by adding a plate on the side, but because of the odd angle of the flywheel system, the axle didn't quite fall on the grid. This resulted in this mess, a bent axle and a sprocket that doesn't quite align with the other sprocket. This, although not aesthetically pleasing, did prevent the chain from falling off most of the time. Because the chain runs over the bands, the band pulls up, unseating the chain and pulling it off. It's hard to show, but it has happened several times. The flywheel system was basically pulled straight over from the camp bot due to the short initial build time. The flywheel spun slower than the initial model due to the V5 motors being 200 RPM and not 240 RPM. Later in the season, once we got a bit more of our V5 order, we switched over to 100 RPM gearboxes. This decreased rev time and increased the time before the motors would overheat, but decreased the RPM to roughly 2500. This decrease in RPM didn't hamper us a lot, as RPM isn't everything in a flywheel. We have found that crush plays a much more important role in the power of the system. Early in the season, we used rubber bands wrapped around the wheels, but we ended up replacing this with non-slip mat zip tied to the wheels, with a couple rubber bands around. This increased the grip of the wheels on the ball, and thus the energy imparted into the ball. In our first test, the ball actually hit the ceiling. We ended up actually decreasing the speed to 80%, resulting in a final RPM of roughly 2000. Early in the season, we used low-strength axles, which were a quick option that had proved themselves at the camp. We did, however, know that the flywheel RPMs are crippled when an axle becomes bent, and this actually happens in regular use. When the ball goes through the flywheels, it pushes the wheels out slightly, which can bend the axles and cause them to need to be replaced. We ended up replacing the axles with high-strength axles, and we had no more problems. This did result in the flywheel being angled slightly higher, as the shaft collars are a bit thicker. This did result in us no longer being able to make across-the-field shots, as the shots would leave the field, but it did allow us to make shots closer to the flags, increasing accuracy. The final addition to the robot was a D-scorer arm. We had an extra motor, so a simple arm to pull off low-scored caps seemed a good option. We actually found that attaching a row of standoffs to the arm would allow us to, in skills autonomous, both intake a ball and flip a cap at the same time. Overall, this may be the robot I'm most proud of having a part in. This robot has proved to be a truly amazing robot, especially when paired with hours upon hours of driving practice and even more hours of autonomous programming. Even though its last match would be a loss, I'm incredibly happy about how this robot performed and how well it was built compared to previous years. It goes to show that a robot that is very much not the meta can prove to be a true contender when it's been continuously improved through trial and error over many months and matches. Thank you for making it this far, and if you're interested in more videos on my experiments with robots, both Vex robots and combat robots, be sure to like this video and subscribe. Thanks so much for watching, and keep experimenting.